I forgot to turn my microphone on, so I'm just going to have to narrate this. We'll see how it goes. It's not going to be live narration anymore. It's going to be narration after the fact. This problem refers to an insulating hollow sphere, inner radius A, outer radius B. Within the insulating material, there's a volume charge density throughout. Now that volume charge density gets larger and larger as R gets larger. So as you go toward the outer radius, when you go from A to B, the volume charge density starts at a finite value and gets larger and larger as you go to B, the larger the outer radius. So I'm going to make a graph of this, and then I'll ask you whether you can use Gauss's law or not. This graph shows how rho starts out at a finite value at A and increases linearly till radius B, to the outside. So larger volume charge density at the outside than the inside. So your question to whether we could use Gauss's law, your answers will come up in a second. And you were approximately equally split between A and B. Either we're going to have to do an integral. B is that we have to do an integral over the whole charged insulator in order to find the electric field at any particular point. And my answer would be Gauss's law is good enough. And so here I'm sketching a spherical Gaussian surface that is inside the charged insulating material. That Gaussian surface has this, because of the spherical symmetry of the charge density, that Gaussian surface has a radial electric field. The electric field either points radially inward or radially outward. It's a positive charge density, so radially outward. And every point on this Gaussian surface is identical. So the electric field, because of the rotational symmetry, so the electric field has to be the same at every point on that Gaussian surface. And so it is easy to calculate a flux. E dot dA is just E times dA, the left side of Gauss's law. And E is constant over the area, so it comes out of the integral, and you just end up with E times the area of that Gaussian surface is equal to charge enclosed over E0. Now the charge enclosed, you'll have to add up the total charge inside the Gaussian surface, and that means integrate from A out to the Gaussian surface of that charge density integrated over volume to get the charge enclosed. This picture just shows the issue if the charge density didn't just depend on R, but actually depended on theta. Like if the top half was positive and the bottom half was negative, then that would be a charge density whose magnitude might or might not depend on R, but which would depend on theta. Different angles, 180 degrees would be a different charge density. So the spherical symmetry of this problem lets us use Gauss's law. The electric field at the Gaussian surface is a constant at the surface pointing outward, and so it comes out of the integral. Integral of dA is, of course, just the surface area of the area of that Gaussian surface. That's just 4 pi times the radius squared. And then for the right-hand side of Gauss's law, we're just going to need the charge enclosed over E0. That charge enclosed we're going to have to get by integration. Integrate from A to R. Volume integral. So 4 pi r squared dr integrated from A to R gives us the charge enclosed. And if we wanted the electric field outside, we would use a Gaussian surface outside the entire sphere, and the field outside would be just like the field of a point charge that was at the origin and had the total charge of this insulating sphere. Where you'd get the total charge of the insulating sphere is by integrating rho dV, in other words, rho times 4 pi r squared dr, all the way from 0 out to B. Since rho is 0 between 0 and A, you just have to integrate from rho of R from A out to B.